Okay, so welcome back to another video. So in today's video, we actually have a little product expansion. The sine of x equals x multiplied by the infinite product series of 1 minus x squared divided by n squared times pi squared. And this little formulation is actually known as Euler's infinite sine formula. This is actually not really heavily used, but this was actually the first use of verification was used for understanding basic complex analysis, even at a level of Louisville's theorem and even with the Laurent expansion near poles. So this actually gives it even more motivation on analyzing more about like complex analysis. So in today's video, we're actually going to prove this little theorem here, deriving this formula here. And it should be an exciting ride. What I'll do is I'll actually use the Fourier series. So first I'll define like f of t is equal to our cosine function. Cosine in particular with alpha of t with a well, not with, but of a 2 pi period. And it's with the interval in between negative pi to pi, also including the condition with that alpha is not a natural number. So this means the definition of a Fourier series is defined as the following. So we have that our function f of t is equal to 1/2 multiplied by our one of our Fourier coefficients a sub naught. We'll get into each terms on like what their what the coefficients equal to eventually, but let me write out this the whole formula out first. So this is defined as the infinite series from n is equal to 1 of a sub n cosine of n times t, and then plus b sub n sine of n times t. Okay, and now let's define those coefficients, and let me first actually define these coefficients in orange instead. So we have first our a sub naught. So a sub naught is actually defined as the integral, well actually first it's 1 divided by pi, then multiplied with our integral from negative pi to pi of f of t dt. Over here should be fine. Over here we have a sub n, which is equal to 1 over pi with our integral from negative pi to pi of f of t multiplied by our cosine of n times t dt. And then last but not least, we have that b sub n is equal to 1 over pi multiplied with our integral from negative pi to pi of f of t, and then multiply with our sine of n times t dt. So let's actually evaluate our terms of our coefficients a sub n, b sub n, and a sub naught. Now notice that because our function cosine of alpha times t is an even function, then you can actually see that our coefficient b sub n is just equal to 0. So we can actually just ignore the b sub n multiplied by sine of n times t. So really, we're actually just left to evaluate these two terms, a sub naught and a sub n. Okay. So let me just write over here. This is 0 since cosine of alpha t is even. Okay, so with that, and then let's evaluate our terms. Using the evenness, then we can actually rewrite some integrals here. So let's start off with a sub n. So really, using the property that it's even, I can actually rewrite this as an integral of so it's 2 divided by pi multiplied by our integral from 0 to pi of so replace the f of t, so we have cosine of alpha t multiplied by cosine of n times t dt. Now we're actually going to use one of our trig properties, so defined as the following. So cosine of a multiplied by cosine of b, which is simply just equal to 1/2 multiplied by cosine of a plus b, and then plus cosine of a minus b. Okay, so we can actually just use this little substitution back here. So when we do this, this means we get cosine of alpha t multiplied by cosine of n times t. This is equal to just 1/2 then multiplied by cosine of, let's see, since they share t, I'll just substitute that outside, so it's t times alpha plus n, and then plus cosine of, so same thing, factor out the t, so we get alpha minus n. So we have that, so I can just substitute that back in. So let's see, going back to here, we have, this is 2 pi divided by, or 2 divided by pi, 0 to pi of 1/2 cosine of t times alpha plus n, then plus cosine of t multiplied by alpha minus n, and then this is dt. Now, we do some further simplification. Just actually, I put an extra close parentheses. It's actually just, no, I'm correct. There's supposed to be one since it closes off this side here. So dt. Okay, so I'll just factor out the 1/2. So this means we get that this is just 1 over pi, and then we have our integral 0 to pi of, let's see, cosine of t. So this is just basically just rewriting the same thing we written out earlier. And this is actually not that difficult to show. So this is 1 over pi, and then you do a u substitution. So this is actually just sine of t, then alpha plus n, and then we just divide that by alpha plus n. Then over here, this is sine of t alpha minus n, then divided by alpha minus n, and we evaluate this with our bounds from 0 to pi. Okay, so here's a little interesting little property you can check to verify yourself, but we want to note that sine of, so when we evaluate this at pi, so we get pi and then alpha plus n. Notice that that's actually just equal to sine, that's also equal to sine times pi of multiplied with alpha minus n. And we can actually write this as an explicit formula since there's that periodicity that exists. So it's -1 to the power n, and then multiplied by sine of alpha times pi. And so when we do this, we can simplify out some more. So far just write a sub n is equal to, let's see, so -1n multiplied by sine, then of pi times n, or that's actually supposed to be an alpha times pi. Okay, and then we divide this by pi, and simply we can just factor some terms out. So we're basically just factoring out, so we get that this is just 1 over alpha plus n, and then plus 1 divided by alpha minus n. Okay, but we can also continue doing a little bit more simplification from here. So what I can do is I can actually just get a common denominator and do the butterfly method. So rewriting from our previous term over here, so this is sine alpha pi and then divided by pi, and then butterfly method, which is just, let's see, alpha minus n, and then plus alpha plus n. Then you just multiply the denominator together. We get that this is just a difference of squares, so it's just alpha square minus n square. And keep going a little further, then we get that this is actually just multiplied, it's just 2 times alpha divided by pi, simply because the n's cancel and we have alpha plus an alpha, and I just factor that outside. And then just multiply with everything from here. So it's just -1 to the power n, then sine times alpha times pi, and then divide by, from this denominator, alpha square minus n square. Okay, and I will just underline this in black to reiterate what our a sub n term is equal to. Now, next, let's actually calculate our a sub naught term, which that actually is a piece of cake to integrate, since this is just in a pretty easy standard definite integral. So let's see, a sub naught is equal to, let's see, I can actually, using evenness again, I can actually rewrite our bounds. So when we do this, our constant outside is rewritten as 2 divided by pi. Then from 0 to pi of f of t, so this is cosine of alpha t dt, which is simply just 2 times pi, well, actually down below is going to be an alpha, then pi, and then sine of alpha times t evaluated from pi to 0. And then simply we just plug pi and 0 into here, and we get that this is just 2 divided by alpha times pi, and then multiply by sine of alpha times pi. Okay, and I will underline our a sub naught in black as well, just to reiterate what our a sub naught term is. So now we found our Fourier coefficients, let's actually substitute that back in. So going back, so we have cosine of alpha t is equal to, so 1/2 multiplied by our a naught, which is just 1 divided by alpha times pi, and then we multiply that with over here, so it's just sine alpha times pi. Okay, and then plus our infinite series over here, so this is the infinite series equals 1 of, let's see, so we have 2 alpha multiplied by -1 quantity to the power n, and then multiply with sine alpha pi, multiply with cosine coming from over here, so n times t, and then we divide this by pi multiplied by alpha square minus n square. But we can also simplify this a little more. So what I can do is I can actually factor out a sine alpha times pi divided by pi, and then you'll see that this actually can be factored out to just 1 divided by alpha, and then plus our let's see, so I'll factor out the 2 alpha outside of our sum, so this is 2 alpha multiplied by our infinite series of, let's see, this is -1 quantity n, then cosine of n times t, and then divided by this is just alpha square minus n square. Now what I'll do is I'll actually divide a sine alpha pi divided by pi to both sides. This means the reciprocal changes, so we get that pi's in the numerator multiplied by cosine of alpha t, and divided by sine alpha pi, and so this is just equal to 1 divided by alpha, then plus 2 times alpha, and then our infinite series. Actually, this is fine for now. I was thinking about putting back the 2 alpha back in, but not just yet. We'll get to that eventually. So n times t, and then divided by alpha square minus n square. Let's see, we can actually plug t. Let me write plug t equals pi. Then we see that we have a sine pi t, and then well, alpha pi and then alpha pi. We can use trig. Then this is actually the same thing as just cotangent. Let's see, alpha pi, and I'll actually subtract the 1 over alpha. So 1 over alpha is over here, and then that's equal to, let's see, so this is 2 alpha and multiply with our infinite series. Notice that if I were to plug t equals pi for cosine of pi, then we get that it's always going to equal 1 for no matter what values of n we choose. So this means this is actually just, the numerator is always just going to be 1, and then alpha squared minus n squared. So now let's actually do a little substitution. So I'm going to let alpha be 1 divided by phi. Do not get confused. Phi is actually a constant, not the golden ratio. So this means we get that this is pi multiplied by cotangent of just phi, then minus 1 over, actually this is actually supposed to be pi divided by phi. So yeah, you see that this is just phi over here. We plug alpha here, then the reciprocal changes, so we have this is just phi divided by pi, and then this is equal to 2 phi divided by pi then multiply with our infinite series. See, this is 1, then divided by. So I'll actually, so this is going to be phi squared divided by n squared. And let me actually simplify this out a little further. So see, we get a pi, we have a, it's supposed to be a pi square on the bottom, not an n square. Pi square minus, so pi square over here, so it means this is get n square, then pi square. Or rather, this is actually the same thing as, 2 phi, then divided by pi. This is 2 phi divided by pi, then our infinite series, and then we just flip we're basically just flipping the reciprocal. So that means pi squared goes on the top, and then phi square minus n squared pi square. Now we can continue simplifying some things down a bit. So let's see, this still stays the same, then minus phi divided by pi. I'll factor out pi outside of our series and then put back the 2 phi from here. So this means this is our infinite series of 2 phi, then divided by phi squared minus n squared, and then pi squared. And now I'll just divide pi to both sides. So this means this is just cotangent of phi. Let me write this a little better. And then this is just, let's see, divided by pi, then this means this is just 1 divided by phi. And then we have our, just our infinite series without the pi being multiplied by. So next what I want to do is let's actually take the integral of both sides. So I'll integrate this between our bounds from 0 to x, and then let's see, so we got cotangent of phi, then minus 1 divided by phi d phi, which is equal to our integral of our series of, let's see, 2 phi divided by phi squared minus n squared pi squared d phi. You can actually see that this series is uniformly convergent between the our bounds from 0 to x, with x being strictly greater than or 0. And you can actually show this by using the dominant convergence and actually compare that to the p series such that p is actually equal to 2. So what this implies is that we can actually swap our order of integration and summation from this side. So, okay, I'll just rewrite the same thing as before, 0x cotangent phi and minus 1 over phi d phi equals to our sum, and then with our integral 0x 2 phi and then phi squared minus n squared pi squared d phi. But this is actually really easy to see that cotangent phi, simply you can rewrite this as cosine of phi divided by sine of phi, take the u substitution, and you actually get that this is actually just, well, let u equals sine phi. Then you'll see that this is actually just equal to the natural log of, well, we're dealing with absolute positive values, so absolute value is sine of phi, and then this is minus ln of phi, okay? Then equals to our series of the natural log of, okay, so this is basically just do a u sub. So we let phi squared minus n squared pi squared equals u. You derive that, you'll see that 2 phi cancels from the numerator, and you'll see that this is actually just ln of phi squared minus n squared pi squared. And then we evaluate this from 0 to x. Simply continuing forward, we can actually use our rules of natural logs to actually combine this into one natural log of one input. So this is just sine of phi divided by phi. Yeah, and that's evaluated at x. And then when you evaluate this at 0, simply it doesn't exist for the natural log of 0, so we actually have to take the limit as phi approaches 0 of the natural log of sine of phi d phi, or sine of phi divided by phi. And over here, this is actually supposed to be an x, since we evaluated it at x right there. So x and then x, okay? And then we set this equal to equals 1, so this is the natural log of, yeah, and then use the rules of natural logs into the bounds, so we get that this is just x squared minus n squared pi squared, and then this is divided by negative n squared pi squared. Let's actually use a couple facts here, and we're almost done with the video. So I want to actually use the little theorem that the limit as, say, t approaches 0 of sine of t divided by t, that's equal to 1. Simply, this is without having to use the L'Hopital's rule, you can actually use that proof. And another property of using natural logs is the natural log, or rather, the sum of the natural logs is actually equal to the natural log of the products, simply because of continuity. So we're actually going to use these properties to fill in the slots here. So we see that this is ln of sine x of x. So okay, so far that this is just this still preserves right here. But we see that if we take this limit, we get that this is ln of 1, which is just 0. Okay, and then over here, we're actually going to use this property, and you can actually, I'm not going to expand the series out and then find the pattern. You can actually check this yourself to see if this this is the formula used here for this product. But this actually comes out that this is just the product, the natural log of the product of n is equal to 1 to infinity of 1 minus x squared minus n squared pi squared, and then, or rather, actually this is just supposed to be x squared on the numerator, and then divided by n squared pi squared. And then if we take the e base, take the exponential to both sides, then ln will cancel out, so we're actually just left with sine of x divided by x equals our product series 1 minus x squared n squared pi squared, and we're just about done. You just multiply the x to both sides and get to the conclusion that indeed sine of x is equal to x multiplied by this infinite product of 1 minus x squared divided by n squared pi squared, like so. Put a check. And there we have it. Alright, that's pretty cool if you ask me.